Hello, my name is Jamie Peterson. I am a Master's of Arts candidate in Medical and Biological Illustration. This is my presentation on my master's thesis, Visualizing Cochlear Specializations that Enhance Protection of Hearing Function in Bats. The cochlea is a fluid-filled coil of the inner ear located in the temporal bone, shown in the bat skull in blue. It transforms sound waves into electrical signals for processing in the brain. The loss of cochlear sensory hair cells and damage to nerve fibers over time cause age-related hearing loss. The 3D model to the right illustrates the external cochlea structures. The house mouse, or Mus musculus, is a common and familiar lab model used for studying the mammalian auditory system. The big brown bat, or Thesis fuscus, exhibits unique resistance to age-related hearing loss, allowing them to use echolocation throughout their lifetime. The focus of this thesis was comparing cochlear morphological differences between the big brown bat and house mouse. There is a lack of educational resources for comparative cochlear anatomy and visual side-by-side comparison of the big brown bat and mouse. The 3D structure of the cochlea is difficult to visualize due to its location in the bony labyrinth and small size. Objectives for this project were to first communicate comparative cochlear anatomy of the big brown bat and mouse by creating an interactive educational resource and 3D cochlea overview animation. Second, to create interactive 3D cochlea models as an educational resource. And third, promote the significance of bat noise-induced hearing loss research and its potential impact on strengthening the understanding of human age-related and noise-induced hearing loss. Primary audience included auditory researchers, neuropathologists, graduate students, and a secondary lay audience with an interest in biology. Types of data used in this project included micro-CT data, which is a high-resolution 3D imaging technique utilizing X-rays. Cochlea serial sections were embedded in plastic and sectioned into 30 micrometer serial sections and stained with toluidine blue. Sources of the datasets included the Lauer Lab, the Whiting School of Engineering, and the McCusick-Nathans Department of Genetic Medicine at Johns Hopkins University, the Pound Human Identification Laboratory at the University of Florida, and the free online digital repositories Movosource and Digimorph. Segmentations of micro-CT and histological data were created using 3D Slicer, Horos, and Reconstruct software. 3D model repairs, sculpting, and additional modifications were created in ZBrush, Cinema 4D, and MeshLab. The wireframes, storyboards, 2D illustrations, and user interface elements were created using Adobe Illustrator, Photoshop, and the iPad application Procreate. The interactive module was created and coded in Adobe Animate using HTML5 and published using WordPress. The optimized 3D models were imported into C4D for lighting, materials, and keyframing. The 3D render frames were added to Adobe After Effects for compositing, labels, and audio. The results of this project included an interactive educational module containing a 3D overview animation and 72 assets, including 2D illustrations, icons, buttons, and annotations. Data-derived 3D models include 6 models for the overview animation and 4 available on Sketchfab. I will now play my overview animation.
The big brown bat, or Thesis fuscus, is an auditory specialist with a broad hearing range and high sensitivity to ultrasonic signals used for echolocation. The house mouse, or Mus musculus, is an auditory generalist with a comparatively limited hearing range. There are remarkable variations in cochlear structure between these two species. The cochlea is a fluid-filled coil of the inner ear located in the petrous portion of the temporal bone. The apex of the cochlear spiral points rostrally towards the mandible, while the base points towards the external ear to receive sound vibrations. The cochlea transforms sound waves into electrical signals for processing in the brain. It is attached to the semicircular canals, which record the angular velocity of head movements to maintain balance. Inside the cochlea, different sound frequencies stimulate sensory hair cells along the basilar membrane. Lower frequency sounds stimulate hair cells in the apex, and higher frequency sounds stimulate hair cells in the base. The length of the coil of the big brown bat is approximately 6 to 7 millimeters, compared to that of the mouse, which is approximately 5 millimeters. The extra half-turn of the big brown bat cochlea supports a broader hearing range. Studying comparative cochlear anatomy can aid in understanding auditory specializations and hearing loss in mammals.
I will now show a demo of the interactive module. On the home screen, the user can enter the module. Under the Cochlear Anatomy button are secondary pages that detail the inner structures of the cochlea. The annotations on the cochlea section and organ and portee pages reveal information about the membrative structures. Under the normal versus deaf bat button are pages for damage data and damage mapping information. Under the Overview Animation page is a link to the animation housed on YouTube. These interactive models are educational tools available to the public on Sketchfab. These models allow the user to see the cochleae and skulls from various views, aiding with spatial learning and structural relationships. My results address the needs for an interactive comparative cochlear educational resource focused on the big brown bat and mouse. A workflow for future biocommunication projects involving animation and interactive module for teaching comparative anatomy. The interactive is linked to the Lyra Lab website. The animation can be found on YouTube with closed captions. The interactive models are available on Sketchfab. All the results are also available on my website. Variation in micro-CT data resolution created artifacts and loss of geometry within the cochlea of each species. The segmentation of multiple bat and mouse specimen aided in the repairs in ZBrush and C4D through structure comparison. Meetings with the Lyra Lab were held to provide feedback on navigation, accessibility of content, and the organization of interactive module. This ensured content was presented in an engaging way for the user. Future directions include additional bat and mouse 3D interactive models of the middle ear ossicles, sagittal cut of the cochlea with membranous structures, and the organ and portee, and an additional interactive model of an adult human cochlea, as well as formal testing could provide user feedback. In conclusion, the results of this project provide a didactic and accessible visualization of comparative cochlear anatomy with an interactive module, 3D animation, and interactive models. Thank you to Amanda Lauer, my preceptor, for helping me navigate through a complex structure, your enthusiasm, and your support throughout this project. Thank you to Lydia Gregg for all the encouragement, guidance, and patience. A special thank you to Madison Weinberg and the Lyra Lab, the Department of Mechanical Engineering and the Department of Pediatrics at Johns Hopkins University, and the Pound Human Identification Laboratory at the University of Florida, the Vesalius Trust for Visual Communication and Health Sciences for their generous support, to all the faculty and staff at the Arts Applied to Medicine for their knowledge and skills necessary to complete this project. Thank you to my family and to my classmates of 2020 for your friendship, laughter, and support. Thank you for watching. I encourage any questions or comments and would appreciate any feedback.